This is your presenter, Asloob Mudassar, and I am presenting slide number 143 of the course on the laser physics. Question is, discuss dye lasers covering their main features. The answer is, active medium in a dye laser consists of a solution of an organic dye, for example, polymethylene, with a wavelength range of 0.7 to 1.5 micron, xanthine, covering visible spectrum. Coumarine dyes with wavelength range from 400 to 500 nanometer in a liquid solvent, for example, water, glycerol, methyl alcohol, ethyl. Rhodamin 6G dye belongs to the category of xanthine and gives peak wavelength at lambda is equal to 590 nanometers. Let's discuss figure number 1. The caption of the figure is plots of triplet absorption cross section, sigma T, singlet stimulated emission cross section, sigma E, and absorption cross section, sigma A, for ethanol solution of rhodamine 6G. So you can see that the wave numbers with 10 to the power 3 times centimeter inverse is plotted on the horizontal axis. Cross section in 10 to the power minus 16 centimeter square is plotted on the vertical axis, and another axis with a wavelength of nanometer equivalent to the wave numbers are shown from 700 to 450 nanometers. So there are 3 plots. One is the plot that corresponds to sigma T, and sigma T is actually the absorption cross section of the triplet transition. So sigma T is the absorption cross section of the triplet case. Sigma E is the stimulated emission cross section for the singlet transition, which we also refer to as the fluorescence case. And then we have the absorption cross section, sigma A, and the absorption cross section is shown. And this absorption cross section, all these 3 curves are shown for the case of ethanol solution of rhodamine 6G. And these are the absorption cross sections that we shall be discussing in detail. Absorption and emission characteristics of rhodamine 6G in ethanol solution along with the stimulated emission cross section are shown in figure number 1, which I have shown you over here. The characteristics can only be explained if the energy levels of a dye molecule are shown. So it is essential that we must know the energy levels of the dye solution before we have a plot of those absorption cross sections. These energy levels are only understood through the free electron model. So we shall see in a few next slides that free electron model is essential in order to understand the energy levels of a dye molecule. Consider the simplest case of a thiamine dye, a molecule of which is shown in part A and part B of figure number 2. So let me show you the thiamine dye first. This is as in part number A and part number B. So let me first of all go through the caption. Application of a free electron model to a dye molecule for its electronic energy states. So you see that here we are applying the free electron model to understand the electronic energy states of a dye molecule. Chain structure of the molecule in part A. So in part A, you can see that it is the chain structure of the dye molecule in part A, and in part linear structure of the molecule in part B. So you can see that this is the linear structure of the molecule in part B, and this linear structure corresponds to the central line of this chain structure. For example, CH3, then N, then C, then carbon, carbon, nitrogen, and then again CH3. So this is the linear distribution from the chain structure of the molecule. So this is the linear structure of the molecule in part B. Potential representation in part C. So you can see that this is the potential representation of this corresponding to this one-dimensional molecule, one-dimensional structure of the molecule. So you see that you can see that this is the potential, which is higher at the left end, and the potential is also higher at the other end. And in between the two high values of these potential walls, you can see that these are the variations in the potential. And part number D is actually the approximate potential well as shown in part number D, as shown in part number C. So the potential which we have shown in part number C, if we can approximate that potential by the potential of a well. For example, this is a D represents the potential of a well, and you see that these high values of the potential is represented by the straight vertical lines on the left hand side and also on the right hand side, and separated by a distance L, where L is the length of this one dimensional chain or this one dimensional linear structure of the molecule. So this is, you see that a square potential that we have shown corresponding to the simplified diagram shown as a potential in part number C. And you see that this is a one dimensional potential, and this is a one-dimensional square potential problem, and the electron can move in this potential. The electrons which are contributed by this chain or by these linear molecules, we shall explain that those molecules could exist in this potential as shown in part number C, or more accurately in potential number D, which is an approximation of the potential shown in part number C. And here the molecules you see can move over here. So we have shown the simplest case of a cyanine dye, a molecule of which is shown in part number A and part number D of equation of figure number 2, which I have just gone through. There are two planar distributions, one above and one below the plane of the molecule, in which pi electrons of the carbon atoms move freely with their movement limited by the repulsive potential of the methyl group at the ends of the dye chain. So you see that here the pi molecules, that is CH3, nitrogen, carbon, again carbon, again carbon, 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 nitrogen, and CH3, which we have shown as a linear one-dimensional structure of the above chain in the center. So the central branch will actually contribute the free electrons, which we call as pi electrons. So the pi electrons will be contributed by this one, and you see that there is a methyl group at the end of each branch. For example, in the central branch at the end there is a methyl group, and on the other side there is also a methyl group, which we have represented as, for example, in this case as CH3 twice, occurring twice, and then of course with the nitrogen molecule, nitrogen with that. So this is the methyl group, and the methyl group, the electron is bounced back due to the repulsive potential of the methyl molecule, and then that is why we have this potential peak. This is the potential which is the repulsive potential in part number C, and also the repulsive potential in part number 3 at the location of the methyl molecule have been shown, which we have simplified in part number D. So there are two planar distributions, one above and one below the plane of the molecule, which we have shown in part number T of the structure, of the linear structure, in which pi electrons of the carbon atoms. So you see that these are the pi electrons associated with the pi orbitals of the carbon atoms move freely with their movement limited by the repulsive potential of the methyl group at the end of the dye molecule. So you see that these molecules are repelled by these methyl groups which are available at the ends of this di chain, and they will repel back, showing a high value of potential there. The electronic states of the di molecule are due to these pi electrons. So you see that when we want to discuss the electronic states of this molecule, then of course the electronic states will arise due to these pi electrons that we are discussing over here. So these pi electrons are actually responsible for the electronic states of the di molecules. The energy levels of these pi electrons are equivalent to those of a free electron in a potential well of the form shown in part number C of figure number 2, or more accurately in part number D. So you see that the energy levels of these pi electrons are equivalent to those of the free electrons. So you see that here we are applying the free electron model of the potential, and then we are having a pi electrons there, and then the energy of these pi electrons will determine the energy levels of the di molecule. For simplicity, the well may be approximated by a rectangular shape shown in part number D. The energy levels corresponding to the well is given by. So you see that this is the energy of an electron, of a free electron in the potential well, and this is En is actually the energy of the electron in the nth state, that is given by n square and then multiplied by h square over 8 ml square, where h is Planck's constant, m is the mass of the electron, and L is the length of the potential well. And n is actually will take integer values and it will give you the state of the electron. For example, if n is equal to 1, then it means that the electron has an energy in its lowest state. The next higher state will be for n is equal to 2. The other next states will be n is equal to 3, n is equal to 4, and so on. So n will take integer values, and corresponding to those integer values, we will get multiple states of the electrons with different energies. Where m is the mass of the electron, capital L is the length of the square well, and n takes integer values. If a di molecule is stable, so you see that here very important point. Since we want to have a stable di molecule, and the condition is that if a di molecule is stable, it would have even number of pi electrons. So at least the least number of pi electrons for to ensure the stability of the di molecule must be 2 in number. Then of course these will be higher in numbers as well. For example, it could be 4, it could be 6, and so on. So even number of pi electrons are required in order to ensure the stability of the di molecules. We are not going into detail of this one, we are just presenting the facts. Let this number be 2. For example, we are assuming here let this number be 2 as the simplest case. So n is equal to 1 corresponds to the lowest energy state where the two electrons have opposite spins, with the total spin equal to 0. So since we are assuming that two electrons are available, two pi electrons are there in the potential well, and these pi electrons are oriented in such a way that they have opposite spins. That is, one electron have spin up, the other electron will have spin down, and adding up the spins together, we have the total spin of the two due to the two electrons will be equal to 0. Considering these two electronic state, considering that only two electronic state exist, the energy of the electron in the second state is obtained by setting n is equal to, which is given over here. So in the previous equation, that is in equation number 1, if you put n is equal to 2, then you will get the electronic states. So this will be the energy corresponding to the electronic states in the second state. So this is that is the equation number 2 will give you the energy of the electron when the electron is in the second state. So in the first state n should be equal to 1. For the second state, n is equal to 2. And you see that here we are only discussing two states of the electrons, because these two states are enough to explain our di laser system. When the total spin is 0, it is represented by the singlet state. For example, S naught is equal to half minus half. That is, one electron has a spin up, and due to the minus sign, the other electron has a spin down. So the total spin is a half plus half minus half is equal to 0, and the mod of that one is equal to 0. So S naught is actually a singlet state. That is the minimum state of the energy. That is the minimum electronic state in which the two electrons with n is equal to 1, that is the lowest possible state, and have opposite spins. That is, the two electrons will have opposite spins represented by the arrow up and arrow down case. This is indicated in the lower box on the left hand side in figure number 3. So let me show you in figure number 3. For example, this is figure number 3. So let me read the caption first. Singlet and triplet states representing energy levels in a dye solution. So these are the singlet states. That is S naught. This is an electronic state, and you see that these horizontal bars present in the S naught are actually the vibration levels corresponding to the electronic state S naught. And the next high electronic state corresponding to the value of n is equal to 2 is S1. So S1 is also again a singlet state, and these horizontal lines in this singlet electronic state are the vibrational levels. So the electronic state S0, which is a singlet state, and the higher electronic state S1, which is also a singlet state, they have many, these are electronic states, they have many horizontal lines representing the availability of the vibrational levels. And in between these two, any horizontal line, and between any two horizontal lines, there are rotational levels which we have not shown. So S0, S1 represents singlet electronic states corresponding to n is equal to 1 and n is equal to 2, and having many horizontal vibrational levels, and of course many rotational levels in between them, which we have not shown in this diagram. And on the left hand side, we have shown two boxes corresponding to S0. You can see in these two boxes, there are two electrons shown with the anti-parallel spins. So one has a spin up, the other has a spin down. And you see that when the two electrons, one has a spin up and one has a spin down, then this is the case of a minimum energy of the electron. So you see that when we provide energy to one of these electrons, what will happen? And one of the electron will take energy, because we only want to raise only a single electron to the higher state. So this is the situation. The electron will go into the electronic singlet state S1. And here you can see that in the box on the left hand side, we have shown the two electrons, one with the spin up and the other with the spin down. But the electron with the spin down has moved to the higher energy state. So you see that here again, the two electrons have opposite spins, though they are lying in different energy states. But again, this is a singlet case. So we have the singlet case S0, in which the two electrons have anti-parallel spins, and both have the same energy. Both electrons have the same energy with the anti-parallel spins. And here S1, in the S1 case, S1 singlet state case, we have the two electrons where one electron has an energy state as that corresponding to n is equal to 1. The other electron has an energy state corresponding to n is equal to 2. The two, and again, but the case is that the two electrons have again the anti-parallel spin, as you can see. So this electron in the lower box corresponds to have an energy corresponding to n is equal to 1, and the electron with the spin anti-parallel spin has a principal has a number n is equal to 2. So this has higher energy. But you see that the spins are anti-parallel in both cases. So both are the singlet cases. So S0 and S2 are the singlet states, because the total sum of spins of the two electrons will be 0 in both cases. And on the right hand side, let me show you that we have the triplet states. Triplet states are the states where the electrons have a parallel spin. But you know that if the electrons have a parallel spin, then the electron cannot stay in with the same energy. So the energy has to be different according to the Pauli principle. And the Pauli principle is what I have also explained this Pauli principle in some of the initial slides of this course. So you can go through those and you can understand what is the meaning of a Pauli principle. So here just I want to show you that the two electrons in the triplet case, that is in T1 state, both electrons are parallel to each other. But you see that there is a separation of energy between the two electrons. The two electrons cannot have the same energy because otherwise they must have the different spins. For example, as in case of a singlet S naught, the two electrons have the same energy but anti-parallel spins. And here the two electrons have a parallel spin, so they cannot occupy the same state. So this is the lower electron, this is the lower electron, this is the higher electron, which means that the other electron in the top box has a relatively higher energy in comparison with the electron in the lower box. And this will form the triplet state because here the spins will add together. That is one half plus one half will be added together, and the total spin of this system will be equal to 1. And you know that the multiplicity is given by 2 capital S plus 1. So since S is equal to 1 in this case, so 2S plus 1 will give you multiplicity equal to 3. That is why it is called a triplet state. So T1 is a triplet state. And again, you see that T1 is an electronic state. And with this electronic state, you can see many horizontal lines. These horizontal lines represent the vibrational states corresponding to the electronic state of T1. And between these vibrational states, there are many rotational states which we have not shown. So the next higher triplet state is shown as T2. And here you can see that we have provided energy to the electron, to the higher electron in the state T1, so that it can move to a further higher state. So here you can see that we have two electrons again in the T2 state, where the one electron is again in the lowest possible state and the other electron has been moved to the higher state. Again, the two electrons have parallel spins, but of course different energies. And again, if you add the total spin will be over these two electrons will be half plus half will be equal to 1, and the multiplicity is 2s plus 1 is equal to 3. So that is why it is called a triplet state, and this is the second triplet state. So you see that in this figure we have shown the singlet states with the multiplicity of both states. Both singlet states is equal to 1, or you can say that the total spin is equal to 0 in both cases for both singlet states, and for both triplet states the total spin of the system is 1. So for the T1 the total spin is 1, for the T2 state the total spin is equal to 1. Of course, the T1 state is lying higher in energy than the S0 state. The reason is that the other electron you see that is shown with higher energy over here. And similarly for the T2 state is lying higher in energy in corresponding in comparison with the singlet state S1. Again, the reason is that the second electron is further higher in energy. So you see that we can raise the electrons, we can raise the system from the state S0 to the state S1, that is from the singlet state S0 to S1 state. This transition is possible under the absorption process. So we shall provide the energy through the pumping mechanism using some laser, for example, some flash lamps, which we shall be discussing in detail in this presentation. So we can move through the absorption process. The electrons can be moved from the state S0 to from the singlet state S0 to the singlet state S1. So these are the very desirable states. And you see that in the arrow I have shown that the electron has been raised to the singlet state S1 to some higher vibration level. So there the electron will decay to the lowest possible vibrational level of the state S1. And then from this lowest vibrational level of the singlet state S1, the electron can move to any of the empty vibrational level of the state S0. And this transition will provide you the emission of a wavelength. So from the lowest vibrational level of the singlet state S1 to any vibrational level, any empty vibrational level of the singlet state S0, the emission will take place, and so the lasing will occur. So the higher, so the higher laser level will be the lowest vibrational level of the singlet state S1, whereas the lower laser level will be any of the vibration level. And of course, the electron from this level can decay to any other, from decay to further lower vibrational levels. And you see that this picture resembles that of the 4-level laser system. So you see that it is also possible that singlet states can move to the triplet state also. So S1 to T1 transition is also possible. And you see that this transition is actually a loss for as far as the lasing process or the emission of the lasing system is concerned, because the population is now will appear in the triplet 1 state. And from the triplet 1 state, the transition is also possible to the T, as shown in the transition from T1 to S0. The molecule can also decay from this triplet state T1 to the singlet state S0. But again, through this channel, there is a loss of laser beam, in terms of there is a loss of a population in the upper state, in the upper vibrational level, in the lowest vibrational level of the singlet state S1, because this is forming an upper laser level, and there will be a loss of a population over here due to S1 to T1 transition. And of course, the laser light will not be as intense because of the decrease in population. So you see that what happens when the molecule is in the T1 state, this emission of the wavelength, this laser wavelength, can also be absorbed by the molecule in the triplet state T1, and the molecule can be raised to the triplet state T2. And again, you see that the population is being used in state T1 and T2. So the population will pile up over here. Although the population will decay after some time to the ground state, and then of course the system, then of course the population will available back at the ground level of the singlet state S0 for the pumping process to make the molecules, or to make the system to go back to the higher energy in singlet state S1. But again, of course, T1 and T2 will provide a loss of population inversion as far as the laser system is concerned. So you see that I have explained a bit about the figure number 3, and the rest of the data and the rest of the explanation will be presented in the paragraphs. So now we are going to discuss over here. We were discussing that even for the singlet state S1, we have again the total spin half minus half will be equal to 0, even for the singlet state S0 and the next singlet state S1. This equation will also hold, that is half minus half will be 0 for the next singlet state also. That is, the two electrons will have opposite spin, because here we are talking about S0. This is indicated in the lower box on the left hand side of figure number 3, which I have explained. That is over here. You can see this box over here, and the two electrons with the anti-parallel spins are available with the same energy. Okay, the upper square box against S0 is empty, as both the electrons exist in the lowest energy state with the anti-parallel spins. For example, if both electrons are present in the singlet state S0, of course the state S1 will be empty. The upper square box against S0 is empty, as both electrons exist in the lowest energy state with anti-parallel spins. If one of these electrons is excited such that it occupies the next excited state without change of its spin, that is, both would have the same spin, anti-parallel spins, the total spin due to the two electrons will still be 0. And the next excited state, excited singular state above S0, is designated by the symbol S1. So the S1, the two electrons, when in the forming S1 singular state, will have the same sum of spins, which is half minus half will be equal to 0. That is, even in the singular state S1, the two electrons will have anti-parallel spins. In the two squares against S1, the two electrons exist in separate boxes with opposite spins. but of course with the different energies. The horizontal lines in S0 and S1 represents the vibrational levels. Now we consider the two electrons when they have parallel spins. Here you can see that the two arrows have been shown parallel to each other with the lowest energy. This will be designated by the lowest triplet state, that is T1. The total spin in case of triplet state T1 will be equal to half plus half is equal to 1. And you see that this is 1 is actually the total spin of the system when the system is in the triplet state T1. So since the total spin is 1 and the multiplicity is given by 2s plus 1, so if you put s is equal to 1 there, then 2s plus 1 will be equal to 3. So that is why the multiplicity is 3. That's why these are called the triplet states. So T1 is a triplet state. But you know that in the parallel spins, these two electrons, in the triplet case, the other electron has been shown in the second upper box. It means that the two electrons have different energies. The energies cannot be the same, as it is not permitted by the Pauli principle. The two square boxes on the right side against T1 show the occupancy of two electrons in the parallel spins. The two square boxes on the right hand side of T1 show occupancy of the two electrons in parallel spins. For example, you can see in the same figure that I have explained. For example, the triplet T1 state, you can see that on the box on the right hand side, I have shown two electrons with different energies, but with parallel spins. The excited triplet state next to T1 is designated by T2, in which the more energetic electron moves to the higher state without change of its spin. The three boxes against T2 represents this state. The horizontal lines in T1 and T2 again represents the vibrational levels in these states, and between these states there are many rotational levels. So here you can see that again in the second triplet state, we have this electron with the same energy as that of the electron in the triplet state 1, but the other electron has further moved to the higher energy state. So in the T2 state, both electron, that is the second electron, will have even higher energy, but you see that both electrons have the parallel spins. It means that the total spin of the electron or the total spin of the system when the system is in the triplet state will be equal to again 1, and this is the case of the multiplicity equal to 3, that is the triplet case. So there are two states, the triplet state one, T1 and T2, and the horizontal lines of course are the lines due to the vibrational levels, and there are many rotational levels in between these between these vibrational levels, which I have not shown. The energy of the second electron in the S1 state is calculated by setting n is equal to 2 in figure number 1, in equation number 1. The energy difference will be delta E is equal to E2 minus E1. So you see that since you have moved a second electron in the energy state T2, the energy difference between the energies of the two electrons will be equal to E2 minus E1, where E2 is the energy of the electron which has been moved in the higher state, that is n is equal to 2 state, and E1 is the energy corresponding to the ground state of the electron, where this state corresponds to n is equal to 1, and the difference of energy between the two states, between the singlet state S0 and the singlet state S1 is given by delta E, which is equal to E2 minus E1. So this gives the difference of energy between the states S0 and S1. Delta E increases when the length L of the chain decreases. You can see from this formula of the energy that L is in the denominator. So when L will decrease, the energy will increase. That is, for a shorter chain of the electrons, the energy of the electrons will be greater. So delta E increases when the length L of the chain decreases. Singlet and triplet transitions are allowed with the delta S is equal to 0. That is, the change of spin is equal to 0 as the selection rule. You see that in the singlet cases, both has spin equal to 0. That is, the states that is the state S0, electronic state S1 and electronic state S1, both have spin equal to 0. So the transition as delta S is equal to 0, that is the change of spin will be equal to 0 when the transition is made from S1 to S0 or from S0 to S1. So delta S will be equal to 0. So this is allowed transition. And in the case of triplet case, that both will have both have spin is equal to 1, that is for the triplet T1 the total spin S is equal to 1, and the total spin for the triplet 2 for the second triplet case is also 1. So both has spin, so both have spin equal to 1, and the change of spin delta S is equal to 0 is also permissible. So the transition from T1 to T2 and back from T2 to T1 is allowed. And similarly, the transition from S0 to S1 and back from S1 to S0 is allowed. But the transition from S1 to T1 is not allowed optically, but this transition can still happen, as we shall see, due to the collisional process or due to the cross correlation, cross linkage between the system. This will be explained. So the singlet to singlet and singlet to singlet and triplet to triplet transitions are allowed because delta S will be equal to 0 as the selection rule. Molecules in the ground state, for example S0, are excited through electromagnetic interaction to some vibrational levels of the S1 state. So this is the ground singlet state, this is the S1 singlet state, and we can excite the molecule from the state S0 to state S1 through some electromagnetic interactions. That is through pumping through the laser or by using some flash lamps. The vibrational and the rotational levels are unresolved and makes absorption spectrum quite broad and quite featureless. So you see that in the figure that I have shown over here, the vibrations are very well separated from each other, both in case of singlet states and in case of triplet states. But in reality, they are very close to each other, and it is hard to see the separation between the vibrational levels. And of course, even not possible to see any separation between the rotational levels, although they exist between any two vibrational levels. So they are very close to each other. So molecules in the ground level S0 and in the excited are excited through electromagnetic interaction to some vibration level of S1. The vibrational and rotational levels are unresolved, which makes absorption spectrum quite broad and quite featureless. That is, it is hard to see even the vibrational states. This explains the absorption spectrum of rhodamine 6G shown in figure number 1. So you see that due to the continuous broadband spectrum, the absorption spectrum of rhodamine 6G is shown in figure 1, which you can see over here. So the absorption coefficient cross section is quite broad, you see over here, quite broader. And this is because the vibrational levels are so continuous are located in a continuous sense, that is they are hardly to be resolved. So that's why the absorption and forming a very broad band. Due to that one, the absorption band is very high, is very broader, as shown in figure number 1 for sigma A. Okay, this explains the absorption spectrum of the rhodamine 6G as in figure number 1. The absorption cross section is sigma A is proportional to mu square. This has been established earlier in the theory on laser physics. So sigma is proportional to mu square, where the dipole moment mu is given by the product of electronic charge and the separation L between the potential well and the separation or the length of the potential well. So mu is equal to EL is determined by the length of the chain and is quite large. So the value of mu is quite large, of the order of 10 to the power minus 16 centimeter square. So the value of sigma A, you can see, since proportional to mu square, it is also quite large. The pi electrons can freely move over a distance roughly equal to the length of the chain. Since the pi electrons can move in the square well potential, the length of the square well potential is equal to L, so the electrons can move very freely over the length of the chain. Molecules from the vibrational states of S1 decay non-radiatively to the lowest vibrational level of S1 in a time which is tau nr, that is a non-radiative time lifetime. Tau will be equal to of the order of 100 femtosecond through collisional deactivation. So through collisional deactivation. So you see that the vibrational states in the singlet state S1 will decay to its lowest vibrational state through collisional deactivation, and this will be a non-radiative decay. That is, the photon will not be emitted in this decay when these vibrational relaxations occur from the higher vibrational level to the lowest vibrational level of the singlet state S1. Okay, the electrons can freely move over the distance over the distance roughly equal to the length of the chain L. Molecules from the vibrational states of S1 decay non-radiatively to the lowest vibrational level of S1 in a time tau nr, which is the non-radiative or non-radiative decay time or non-radiative lifetime, which is of the order of 100 femtosecond through collisional deactivation. The molecules then decay radiatively to some vibrational level of S naught. So you see that as I explained that the decay from the higher vibrational level to the lowest vibrational level in this state, in the singlet state S1, is through collisional de-excitation, and this is a non-radiative decay time with a time of the order of 100 femtosecond. But when the population has gathered at the lowest vibrational state of S1, then the transition will occur to any vibrational, any empty vibrational state or any vibrational, any empty vibration level of the singlet state S1, and the emission in the form of laser will take place. And this will form the laser emission. So the upper laser level is the lowest vibrational level of the singlet S1, and the lower laser level will be any vibrational level of S0. Large value of mu gives a large value of the stimulated emission cross section, because both quantities are related. So when a molecule is in the lowest vibrational level of S1, the transition from S1 to T1 is referred to as the intersystem crossing. So you see that this transition violates delta S is equal to 0. So this is not optically allowed transition, and this transition, if occurs, will occur through only intersystem crossing and can occur due to collision. So the main reason is the collision of one molecule with the other molecule. Then according to that collision, under such a collision, intersystem crossing occurs and the transition from S1 to S1 to T1 could be possible. When a molecule is in the T1 state, there are two paths from T1 to S0 by near resonant energy transfer collision, which I have shown. For example, the transition from T1 to S0 has been shown over here. The other possible transitions will be from T1 to T2 by absorbing the photon of the laser. So when a molecule is in the lowest vibration level of S1, the transition from S1 to T1, referred to as the intersystem crossing, can occur due to collision with another molecule. When a molecule is in T1 state, there are two paths from T1 to S0 by near resonant energy transfer collision. So again, you see that this transition is again due to collision because delta S is equal to 0 is being violated by this transition. Or by T1 to T2, this transition is optically allowed because the delta S will be equal to 0 in this case. That is, both will have the same spin. So T1 to T2 transition is possible by absorbing the stimulated photon That is the photon of the laser system or laser transitions. The transition from T1 to T2 is at the expense of transition from S1 to S0. That is, you see that when this transition from T1 to T2 occurs, then the transition from S1 to S0 is compromised or becomes slightly weaker, because the population now has gone not from S1 to S0, but has gone from S0 to S1 to T1, and then from T1 to T2. Because this is a double loss. One loss is that the population inversion has lost due to this transition from S1 to T1. The second loss is that the laser photon has been absorbed by the state T1, and the state T1 has converted to the state T2. So a loss of a photon is also possible, and due to S1 to T1, a loss of a population inversion is also possible. So there are two losses due to these collisional processes. So the transition from T1 to T2 is at the expense of the transition from S1 to S0, and it may seriously obstruct the lasing action. The lifetime for the transition S1 to T1 is much longer than the transition from S1 to S0. Thus, the decay of S1 by fluorescence is dominant. Since S1 to S0 is faster transition in comparison with the S1 to T1, so S1 to S0 transition is a fluorescence transition. Thus, the decay of S1 is by fluorescence, which is dominant in this case. The fluorescence quantum yield, that is the number of photons emitted by fluorescence, divided by the number of electrons raised to the S1 state, is close to unity. So you see that the fluorescence, this emission from S1 to S0 is actually a fluorescence emission. And you see that this corresponding to this fluorescence emission, you can see in figure number 1 that I have shown the fluorescence curve over here. The second is that the quantum efficiency for this transition is very high. So the number of photons that are emitted in this emission process are divided by the number of photons absorbed from S1 to S1 is nearly unity. That is so we can say that S1 to T1 transition are rare depending upon the conditions of density of the molecules. Okay, the fluorescence quantum yield, that is the number of photons emitted by fluorescence divided by the number of molecules raised to S1 state, is close to unity. The lifetime of the triplet state tau T depends on the dissolved oxygen in the dye solution. So note, this point is very important. The lifetime of the triplet state tau T depends on the dissolved oxygen in the dye solution. For an oxygenated solution where the oxygen is abundant, then tau T of the order of 10 to the power minus 7 seconds, compared to the deoxygenated solution where lifetime of the triplet state tau T is of the order of 10 to the power minus 3 seconds. So you see that in the case of deoxygenated solution, the lifetime is much larger in comparison with the oxygenated state of the molecule. So these are the typical values. The singlet and triplet states of a dye solution shown in figure number 3 are reproduced in terms of the configuration coordinate as shown in figure number 4. So you see that, let me show you figure number 3. This is the figure number 3. Now I am going to show this figure number 3 in terms of the configuration coordinate system, where on the horizontal axis you have the atomic separation, and along the vertical axis you have the atomic states shown in curved along with the vibrational levels. So this is the configuration coordinate system diagram. So this is the figure number 4, energy level diagram of a die in configuration coordinate system. And here again you see that this is reproduced from figure number 3. Again you can see that there are two triplet states represented by S0 and S1, and in the form of these parabolic shapes containing many vibrational levels there. The rest of the things are the same, and again there are two triplet states, T1 and T2. So the rest of the things are the same as shown in figure number 3. So this is just the figure that I have shown you in the configuration coordinate system, so that you can see the how this will look like in configuration coordinate system. The vibrational levels in the excited singlet state S1 rapidly decay to the lowest level of S1, and the population accumulates in this level very rapidly. That is in the lowest possible, in the lowest vibration level of S1, the population gathers there and accumulates there in the lowest vibration level of the singlet S1 state. The lowest level of S1 thus acts as the upper laser level. The transition from the upper laser level, which is the lowest level of S1, to some vibrational level, which forms the lower laser level of S0, that is any vibration level of the S0 will form the lower laser level, results in the lasing, that is in the fluorescence process. And the lower laser levels rapidly decay to the vibrational levels of S0. So from when the laser transition takes place, then you see that it takes place to the upper vibrational level, and then these vibrational levels decays to the ground vibrational levels very quickly. So under that condition, the system thus acts as a 4-level laser system. So this system, for the case of a die, under this condition, having two singlet states and two triplet states, and the transition between these singlet states in the form of absorption and emission of wavelength in the form of fluorescence will act as a 4-level laser system. The product sigma tau, that is the product of stimulated emission cross section multiplied by the lifetime of the S1 state for the rhodamin 6G, is 3 orders of magnitude smaller than that of the ND-YAG laser. But due to much smaller value of tau, the pump power requirements, which is proportional to 1 over tau, since tau is smaller, the pump power requirement becomes larger. So becomes the pump power requirement for this dye laser system becomes significantly larger in comparison with the ND-YAG laser, which is slightly compensated by the large value of sigma. So you see that I have discussed earlier in the previous few pages that sigma is very large. But of course, the smaller value of tau is compensated by some larger value of sigma. But even then, a very strong pumping is required. The inter-system crossing, that is from the singlet state S1 to the state T1, raises the population of the triplet states under the transition from T1 to T2 transition, occurring at laser wavelength. So this transition T1 to T2 occurs at a laser wavelength, which is a second loss to the laser beam. Let KST. So ST stands for the transition from singlet to triplet, and K is actually the inter-system crossing rate. So KST is the inter-system crossing rate from the singlet to the triplet state. And let NT, capital N and capital T, and N2 are the populations of the triplet states in the upper laser level and upper laser level respectively. So N2 is actually the population of the upper laser level present in the S1 state, in the lowest vibration level of the S1 state, and NT is actually the total population present in the triplet states. So NT is the triplet state population either present in T1 or T2, and the population of the population due to inversion which is present in the S1 state probably in the lowest possible vibrational states will be represented by N2. Okay, so the steady state, which is a continuous wave operation, requires that the rate of decay of the triplet population should be equal to the rate of increase given by this transition due to the intersystem crossing. So you see that in the intersystem crossing, you can see. So due to the intersystem crossing, what happens is that there is a loss of a population inversion. And the second is that due to loss of a population inversion, some transition is taking place from S1 to T1. So some population will be available in T1, and that population is raised to the T2 states due to the laser photon being absorbed by this transition. So there are two losses. One is the loss at the population inversion, the other is lost at the laser photon. So you see that this loss will be compensated by when these will decay to the finally to the lowest energy to this lowest singlet state S naught. Then of course these populations which are trapped in the T1 and T2 state at T1 and T2 triplet states will ultimately come to the S naught state through the transition as shown from T1 to S naught, and then of course the population in the ground state will be available for the absorption to go to the state S1, and that will be compensated. So this compensation requires that the rate of decay of the population of the triplet in the triplet state, which is Nt over tau t, will be equal to the gain which is lost due to the transition from S to T. So the population which was lost, and to that is the population in the S1 state which was used, which were to be used in the process of the lasing action. But of course, some population has moved to the from the S1 to T1 state, and K S to T takes care of that transition. And this loss you see that will appear in this one, and when this transition will decay, that is the rate of decay of the population in the nt that is in the triplet states, the rate of a population in the triplet states will of course will compensate the loss due to that one, which is due to kst times n2. And I have explained that these transitions from the triplet states will ultimately come back to the ground state, and where the transition from the under the absorption case will occur to from S0 to S1. So that will be compensated. And here we can solve this equation for the case of tau t, which is equal to 1 over k st multiplied by nt over 2, nt over n2, where tau t is the lifetime of the triplet state. Laser action requires that the gain coefficient, which is sigma E times N2 due to the stimulated emission, and also this is also valid for the stimulated absorption, must exceed the loss due to the triplet absorption. So you see that the laser action in the continuous mode will only be possible when the transition in the form of when the laser emission from the this is the laser emission cross section, which is sigma E stimulated emission cross section multiplied by N2, when this term dominates the term due to the loss, because sigma T multiplied by Nt is a loss of the population in the triplet states. So when the gain is much greater than the triplet states, then of course the continuous wave operation of the system will be possible. And we can solve this equation for the ratio of sigma E to the sigma T, which is greater than Nt over N2. Now we can combine the two equations. That is, we can combine equation number 3 and we can combine equation number 4 together, and then we can solve this equation independent of the population of the levels. So tau t should be less than of sigma E to the ratio of the sigma E to sigma T times kst. So if this condition is satisfied, this condition will ensure that is the triplet, that is the lifetime of the triplet state should be less than the ratio on the right hand side. If this condition is satisfied, then of course the continuous laser operation can be ensured. That is the satisfaction, that is the equation 5 must be satisfied. And you know that the right hand side of equation 5 is independent of the population in the triplet states as well as in the singlet states. This condition ensures CW laser operation. If this condition is not satisfied, pulsed laser operation can still be achieved. So you see that if this condition breaks down, then of course we can go for the pulsed laser operation. The pump pulse duration should last for a time before a significant population gathers in the triplet state. So you see that we must ensure the pulses to be emitted, and the pump pulse duration should be such that it should complete that is the pumping pulse should complete its duration before a significant population gathers in the triplet state for the pulse operation to be ensured. Pumping process can produce the thermal gradients in dye solutions, which results in optical distortions. These distortions may prevent the lasing action. Due to lasers, uh, dye lasers are pumped with flash lamps, which are arranged at one of the foci in the elliptical cylinder. So if our cavity is in the form of the elliptical cylinder, then the flash lamps can be located at one of the foci of the elliptical geometry, and the dye solution is made to flow through a glass tube located at the second ellipse focus, or at the second foci of the ellipse. For more uniform pumping, annular flash lamps consisting of two concentric glass tubes are used. Dye solution is made to flow through the central glass tube. This geometry provides better and symmetric gradients of the refractive indices. So improved geometry can be obtained by using two concentric glass tubes. More intense and pulsed beam from a nitrogen laser is used in pulsed dye lasers as the pumping source. Excimer lasers are equally useful as the pumping source in the UV for improved arrangement, for improved average power from dye lasers. Pump lasers to dye lasers. Pump lasers to dye laser output conversion efficiency is better in visible compared to the UV. With pumping using lasers in visible, dye degradation can be minimized. Transverse laser pump configuration is also used, in which pump beam is focused on a dye cell in a direction orthogonal to the resonator axis. And of course, when we talk about the transverse laser pumping configuration, then of course it will be orthogonal to the resonator axis. A cylindrical lens is used to focus the beam as line. So you see that here we are focusing, here we want to have a line focus beam. A cylindrical lens is used to focus the pump beam as line, with the line focus length equal to the length of the dye cell. So the pump beam can be focused as a line beam on the dye cell using cylindrical optics. The transverse dimension of the line focus is smaller than 1 millimeter, as a diffraction grating at grazing incidence is used inside the laser cavity to tune a particular wavelength from within the available bandwidth of the pumping source, that is from 30 to 50 nanometers. So if you have even a laser operating giving you a bandwidth from 30 to 50 nanometer, you can choose this arrangement to select one of the particular wavelength. The arrangement is shown in figure number 5. So first of all, let me go through the caption of the figure. Schematics of transverse pumping for a dye laser using either nitrogen laser or copper vapor laser or excimer laser. So three types of laser can be used as the pumping sources for the dye lasers. So you can see over here that you have, so let me show figure mirror one. This is mirror one. This is the beam spot as a beam stopper. And this is the pump beam coming and being focused as a line beam on the dye cell. And you see that this is actually a spherical plus a cylindrical optics contained in this box. And this is focusing as a line focus on the dye cell. And then you see that you have the mirror one, which is the cavity mirror of the laser system. And then you have the mirror two, which is the second cavity mirror of the laser system. And then you see that you can use the mirror number two as a tuning mirror so that you can select a wavelength of your choice from the laser system. So you see that many wavelengths could operate in the laser system. A broader wave bandwidth is available, and using the arrangement that I have just shown in figure number 5, you can select any one of the particular wavelength in the range, for example, from 30 to 50 nanometers. The explanation of this one is given in the next paragraph also. So actually I have missed page number 13, and you see that in the page number 13. Okay, I have seen that the page number 13 is missing, and in that page the description related to this figure was given. So let me explain that. So you see that this is the mirror one. So mirror one and mirror two actually form a laser cavity. So we have a mirror one and we have a mirror two forming a laser cavity, and then we have, you see that we have a grating in the cavity, and we can tune the mirror two. That is, we can tilt the mirror to in order to select required wavelengths from the broader spectrum that we have shown in the previous slide, that is from 30 to 40 nanometer, which was available bandwidth, and we can select any, you see that any wavelengths out of this one by tuning the mirror to shown in figure number 5. So we can tune the mirror number 2, and we can have our desired wavelength to be lasing in the laser tube. Okay, the next para, since page number 13 is missing, and the page number 13 was describing the was also describing page number 14. So let me show you. So let me explain page number 14 by myself. So this is figure number 6, and this gives you the schematics of the continuous wave dye laser pumped with the argon ion laser or with the krypton ion laser. So here the pumping is done for the continuous dye laser operation by the either by the argon ion laser or by the krypton ion laser. So you see that here I am showing you the pump beam. The pump beam is incident. The pump beam is either the argon ion beam or the krypton ion beam is being incident on the mirror number 4, mirror M4. And from this M4 mirror, the light is reflected towards the jet of stream. This is a jet of stream of the dye laser. So the dye laser is over here in the form of a jet of streams at Brewster angle. So Brewster angle to the axis of the to the Brewster angle to the mirror, to the light which is reflected from the mirror 4, that is the pump beam. So this jet of stream which is at an angle of Brewster, which is at Brewster angle, and it is at a Brewster angle to the beam, to the pump beam, not to the laser cavity beam. And you see that the laser cavity is formed by the mirror M1, M2 and M3. And here you have the birefringent filter. Birefringent filter is used to select, is used to tune and to select a particular wavelength to oscillate in the laser cavity. And then of course you can obtain a laser, a tunable output laser from mirror M3. So I would try to place place page number 13 as an appendix to this presentation. So you see that this was all about the dye lasers that I have given. So you need to go through these dye lasers very carefully, and you can, I hope that you will be able to understand many things. I have skipped many things because you see that those things are not very much relevant, and otherwise the presentation would be very long. So I have presented only the necessary data in this presentation to explain the dye laser. So this is the end of slide number 143.